we are ready to go. By the way, we won't record the industrial lecture later, but this one is still going to be recorded. All right, then over to you, Bruce.
Thanks, Frank, and thanks to the organizers for having me. So what I will be doing is going through the most important tenets behind the discovery of the Higgs boson, the first measurements. So that will give an overview of what are the experimental issues pertaining to the Higgs boson. So I'll first quickly go through the graphs of the discovery, and I'm going to unpack those in terms of a number of important steps that will include decays and production mechanisms. Then I will be talking about the measurement of the mass, signal coupling and strength measurements, and if I have time, spin CP quantum number measurements. Now, does anybody know who this gentleman here to my right is? The guy to the right is me, which much fatter and much less white hair. But who is this guy here? Does anybody know?
Is Angler?
That's, excuse me, I couldn't hear that.
Yeah, it's Angler. Someone also typed in the chat.
Oh, okay. Yeah, it's Francois Englert, correct. So this picture was taken in Orsay. The Higgs discovery had already been announced. So that was a conference that came after, but we hadn't yet determined that the spin CP quantum numbers were consistent with those predicted in the standard model. So that was the last hurdle for him to get the Nobel Prize, him and Peter Higgs. So he was very, very interested in attending every conference possible to understand when that was going to be announced. Anyway, so let's dive into it. As you all know, the SM-like or the Higgs-like or SM-Higgs-like boson was announced in July 2012, July 4th. Both Atlas and CMS reported 5 or more sigmas. Atlas reported 5, and then the paper was 6 because we added later the WW. I will spend more time on Atlas because I'm a member of the Atlas collaboration and I can answer more technical questions. And these were the graphs that were submitted to physics letters, indicating a very clear, if you look at the p-value, which is the level of incompatibility of the data with the background-only hypothesis, it was clear that something had been seen in many different channels in a search for a standard model Higgs. So let's try now to unpack all this. What are the elements that this is composed of? And then depending on the time, I will be talking about what measurements have been done that are relevant to establishing that what we saw is compatible with the standard model, Higgs boson. All right, so let's first start with the case. All right, so in the standard model, what you're going to see is that the Higgs boson has a 3-level coupling with W and Z bosons, but also fermions, and those play, of course, a very important role in determining the search strategies, in addition to a very important channel that I will be talking about in a minute, which is more rare, but played also a very important role in the observation and subsequent measurements, which is the loop-induced decays. Now, all the couplings here are within the standard model, and if you know the mass of the Higgs, everything is extremely well defined. So in a sense, it was a very well-defined search. Now that we're looking for physics beyond the standard model, now that the standard model, so to say, has exhausted all its fundamental predictions, the situation is more complicated. But back then, we had some indirect evidence for the SM Higgs boson. We knew a lot about it and continue to know, of course, theoretically. And this was a very well-defined search. And I should also add that it played a very important role in the design of the detectors. And that will become clearer in a minute. Now, it's back when the Higgs was being searched obviously the sensitivity of the SM Higgs mass to loop corrections was logarithmic. But you sort of kind of knew where the SM Higgs was going to be. So if you look at this area of interest, you can see that nature was in fact quite kind to us, in that a Higgs boson around 125 GeV, and this is a branching fraction, so the probability of the SM Higgs boson to decay. We have quite a number of final states that would allow us to understand the Higgs boson and to observe it, where the gamma-gamma branching ratio, which sits at around 2.2 10 to the minus 3, was in fact large enough to be important and very important in the discovery, as we will see in a minute. Now, that's as far as decays are concerned. Now you have to look at how the Higgs is produced in hadron-hadron colliders. You've seen already the picture of how particles are produced in a proto-proton collision, how these are calculated. This already started on the first lectures. The main production mechanisms are depicted here in terms of the incoming partons and the leading order matrix elements, or the leading order Feynman diagram, so to say, for the gluon-gluon fusion being dominant, vector boson fusion, and the associated production, all of which contributed and contribute to the production of the Higgs boson and the stellar model at the LHC. Now, in terms of cross sections, because of the fact that there's a lot of gluons in the proton, and that has been discussed in this school already, the direct production of the Higgs boson, the single direct production of the Higgs boson through gluon-gluon fusion through a top quark loop is basically dominant. You can see here the cross section as a function of the mass of the SM Higgs boson, where the vector boson fusion, which is in red, is subdominant, and then other production mechanisms also play a very important role. So depending on the decay and the production mechanism, you devise different experimental strategies. And I will show some examples of how this was done. In terms of the cross sections here, you've got basically the relevant cross sections in picobarns. This was the central mass energy that was used, that the LHC was running at when the Higgs boson was discovered, and a lot of its properties are now being measured with a higher center of mass, where there's a lot more being produced. But I'm going to concentrate on the early stages of the observation and first measurements. All right, so let's look at the main channels. When I say main channels, these are the channels that were more prominent experimentally to observe it and provide the first measurements that I will be talking about in the next half an hour or so. All right, so the diphoton channel played a very important role, because even though it's loop induced and therefore is suppressed compared to other decays, the branching ratio is big enough, and as I said, around 2.2 10 to the minus 3. It looks small, but because the Higgs boson is produced at the level of tens of picobarns, you certainly produce enough to be able to see a narrow structure. And the reality is that because you are able to detect the energy and angles of the photon, and I will talk about that in a minute, in more detail from the experimental point of view, you're able to basically reconstruct the invariant mass. So you're basically left with the ability of reconstructing the Higgs boson mass, which is very powerful in terms, for instance, of measurements, but also the fact that if you're able to see a narrow resonance, backgrounds are heavily suppressed. Now, these backgrounds and everything that I'm talking about basically has been looked at and studied for decades. Remember, the Large Hadron Collider was conceived in the 80s, and there was a tremendous amount of work in the 90s to design detectors. So all these things had to be understood from the experimental and theoretical points of view. You have quite a number of processes that would give you non-resonant photons. whether it is through direct photon production or through non-perturbative processes. And also, very importantly, is the fact that you can see, despite the excellent detectors and performance of ATLAS and CMS, you're also able to see a fraction of the events coming from a quark that has fluctuated into a pi knot, and a pi knot decaying into 2 photons that are relativistic. So you basically are not able to really completely reduce that background. You know, once the 2 photons are collimated and together, they look like one. So that's really what you have to pin down and understand. So one of the key ingredients for design of the detectors for both ATLAS and CMS, I will spend more time on ATLAS, is basically to design a detector that is able to collect data with very high frequency. Remember, the LHC provides collisions every 25 nanoseconds, and at the same time provide, you know, very good resolution so that we are able to see these nice peak structures. Now, this is all done with Monte Carlo at the time, but Monte Carlos during the LHC era have become extremely accurate, unbelievably accurate compared to predecessor experiments and accelerators. So Monte Carlos have played a very important role in the Higgs discovery. And typically you know, this is a kind of resolutions you are basically able to achieve. ATLAS is slightly worse, somewhat worse than CMS. CMS is better resolution, but basically looking around about a 1% resolution experimentally. ATLAS is slightly above 1%, CMS is somewhat below 1%. And then a very important issue here is basically to understand where the photon came from. That's what we call photon pointing, because if the photon hasn't converted, you have to really do a lot of work to understand where it came from, and that's a very important ingredient to the calculation on the invariant mass. So in terms of ATLAS, you basically have different measurements that allows you to backtrack back to where the photon came from, and this is the tremendous amount of work that had been done over the years to really create the best possible resolution. This is basically different methodologies that I'm not going to get into in terms to try to pin down and measure where the photons came from, where the vertex is, and you can see the significant impact on resolution. A very important aspect of the reconstruction of 2 photons is the fact that especially ATLAS has a lot of inactive material before, or significant, not a lot, but significant amount of inactive material in front of the detector. So what's going to happen is that at least one of the photons is going to convert, and that creates quite a complexity, because you really have to understand the complexity of how these are going to be decaying in the detector, how they're going to be created, and how you're going to reconstruct that pair, and so on and so forth. And you can see here basically also the impact, despite the tremendous amount of work, is you always have a worse resolution when at least one photon is converted. As I said, this work basically took decades to complete, and by the time we started taking data in 2010 and attacked the problem of the diphoton reconstruction, a lot had been learned already. Backgrounds, as I said earlier, they are very important. I mean, yes, it is a sideband analysis, but a lot of effort was put into understanding the composition of the background. We just didn't want to have a sideband and that's it. We really wanted to understand what the sideband is composed of, what the backgrounds are composed of, and a number of techniques were developed for years and then implemented with the data taking. And yes, I mean, the good news, because of the excellent detectors that ATLAS and CMS have, most of the background is really 2 real photons, but you have a contribution from gamma jets and jets that you need to pin down. And the good news is that overall, all these data-driven techniques were basically giving results that were compatible with the data. All right, and this now comes the concept of categorization. This is something that was developed in the 2000s when people realized that we could, yes, we could search for just a bump, But if you start categorizing photons according to certain topologies, like for instance, vector boson fusion or the resolution, you're basically able to improve your sensitivity. And actually, you can write down the formula of the significance. And if you have different corners of the phase space where the signal to background have different ratios, by categorizing the phase space, you will always get a better answer. And this concept of categorization became basically a part of searches in general, and the discovery of the Higgs boson in particular. You have here an example. We introduced with data categorization that were gradually being improved towards the final analysis that was used for discovery. And we continue to have those categorizations, even now much more complex. You basically categorize in terms of the rapidity of the photon. The central pairs will have better resolution than when one of the photons is forward. So all those things are performed, and also the transit momentum plays a role. And this is basically what you see. This is with the full round one data. What you see there, once you do all these things, there's really a lot of complexity and work that went into it. You see basically a smooth distribution with a background that is fit with some function. There's a lot of work that goes into understanding that. You clearly see a very nice structure here, and overwhelming excess of around the 125 that is compatible with the Higgs boson signal. Now let's look at ZZ. That's another very important channel. As I said earlier, the Higgs boson, the standard model, has 3-level couplings to W's and Z's. Again, the advantage of this channel is that the Z will decay into leptons, electrons, and muons that use typically, and then you're able to also reconstruct the mass. So that's very, very important. And then you have a bunch of irreducible backgrounds. You have non-resonant Z production, whether it is from this kind of diagrams on the left, or whether it is loop-induced. All those things are very well known in the standard model. But you also have, of course, nasty backgrounds that that you can control easily, as we will see in a minute, where you have, for instance, in top events, you have a big quark. The big quarks can hadronize into B mesons, and these subsequently decay semi-leptonically, giving rise to 4 leptons, in which some of them come with some hadronic activity, and the same thing with the Z in association with BB bar events. So a lot of work went into understanding how to suppress these and also predict them. As I said earlier, so because you have 4 leptons that carry with which you can reconstruct the invariant mass, you also end up having narrow resonances, which is also very attractive. Again, I'm showing Atlas here, simulation work, Higgs to 4 leptons, Higgs to 4 electrons, and Higgs to 2 electrons and 2 muons, where, okay, the electrons, of course, radiate a lot, so there's a lot of Bremsstrahlung. Not all of it is recovered. As a result of that, the muons have displaced somewhat worse resolution than with the muons, but all those things are relatively understood. And then what people did for the discovery, since we obviously have a very well-defined hypothesis, is to assume that one of the Z's will be on shell and assign to it the mass of the Z, and that obviously further improves resolution. In terms of the reducible background, as I said earlier, you really have to control the production of 4 leptons with some hadronic activity mostly from semi-leptonic B mesons, from the hadronization of the D quarks. And you can see here kinematic distributions in events where the 2 leading leptons, in this case on the left-hand side, 2 leading muons, are accompanied with a pair of muons or electrons that are not isolated. And you want to do that, and experimentally what they do is they sort of probe the data by requiring certain hadronic energy around that electron or muon without compromising the actual measurement of the kinematics of the electron and the muon, but with something around, and that will basically be populated by the backgrounds you want to understand and suppress. And there are different techniques that you use to use these distributions to predict what's the residual contribution of these nasty backgrounds in your final signal. And all in all, you know, even the Monte Carlo worked fairly well, although we were always data driven, but Monte Carlos have always described at least the shape of the kinematic distributions quite well, which was remarkable. And these are basically distributions of the invariant mass of all leptons in the final, and that's the final product, quote unquote. This is run one data. You can see here in around 125 this overwhelming signal that clearly is incompatible with the background hypothesis, which is the red and the purple. And you basically clearly see this very nice narrow structure. And now, of course, we have a lot more events because we have a lot more luminosity and a higher center of mass, but this is really overwhelming in terms of evidence. All right, so the next channel, which is also extremely important, even though with this channel you cannot reconstruct a narrow mass, this is the channel that actually provides the most statistics. I mean, the channel that with which we can track the most number of Higgs events. So it was absolutely essential that it be a part of the discovery and that be a part also of whatever measurements you can do with it. Although, as we'll see in a minute, this is a much more contrived search compared to gamma, gamma, and ZZ for reasons that will become clearer in a minute. Now, as I already indicated, the Higgs boson has a tree-level coupling with W's and Z's, so you have that here. But unfortunately, the W's, because their charge will decay into a lepton and a neutrino, so what you have in the final state are two charged leptons, typically electrons and muons, and some missing energy that is carried by neutrinos. And missing energy is a bit of a nasty thing because you can only see the recoil in the transverse plane. You don't really know what is the energy that was carried along the Z direction. So you cannot reconstruct the invariant mass. Unfortunately, that's really a shortcoming of proton-proton collision. You don't really know what went down the beam pipe. You don't really know basically what is going in the Z direction if you don't detect it directly. And neutrinos are very weakly interacting particles that don't leave a trace in the detector. So the only way you can determine whether some neutrinos escaped is through the balance of transverse momentum in the transverse plane. So that obviously imposes certain restrictions on what you can do with it, but it's very copiously produced. As you will see, there's really quite a number of events there. The backgrounds will be top related, so anything that really produces W's, and you will see in a minute the composition of the backgrounds and basically non-resonant production of W's with different production mechanisms, which are very well known theoretically, by the way, with very, very good Monte Carlos. All right, so one of the important things here, as I said, experimentally, that required, I mean, remember, we started taking data in 2010, and the discovery already took place in the first half of 2012. So a tremendous amount of work had to go into understanding the entire detector. Because the neutrinos don't interact very weakly with the detector, essentially they don't interact, they're only traces. In order to understand whether neutrinos escaped, you have to understand the entire detector very well to really establish that a neutrino or neutrinos escaped. Because what you're going to do is you're going to do the sum of the transverse momentum of all the particles in the detector, and that's a big mess because protons are high energy laden mess. And you have to basically understand pretty much almost everything to, down to round about a GeV or so. So that's very challenging. And the fact of the matter is that the ability of both Atlas and CMS to understand that quantity was actually amazing. I mean, I basically personally had been working on missing interior construction for almost a decade, and we were, very nicely surprised by the ability of Monte Carlos to really describe this very complex quantity. And I just wanted to basically point out to you how complex it is to get this right. So what happens in this search is that the backgrounds depend strongly on what we call jet multiplicity. And this is something very specific to this search, in that in gluon-gluon fusion, you can see here, in gluon-gluon fusion, when you have the Higgs being produced in gluon-gluon fusion, the Higgs is a colorless particle, doesn't radiate, it decays into colorless objects, so that is not going to radiate. It's not going to give final state radiation. So for that part, of the final state, you're going to have depleted jet activity. You're going to have initial state radiation, and that's very well understood theoretically. But when you look at the production of 2Ws from the decay up top, you can see clearly that there is really a lot of jet activity. So in order to search for this channel, we devised what we call jet binning, or the categorization of the search according to jets. And for the discovery, we only looked at a type of events with what we refer to as the full jet veto. Later, when we started measuring properties in more detail, we added more beams. But for the discovery, we really we heavily relied on the zero jet bin here, the first one. And basically, the methodology is the same as the one that we introduced for the photons. You introduce categorizations where in different corners of the phase space, you have different signal to backgrounds. And in this sense, the sensitivity to the observation of the Higgs is really concentrated in the zero jet beam, where the top background you can see here in yellow is the smallest, and the biggest background becomes the non-resonant double production. Then what you do, and actually we spent, even my team back at the time, we spent years, about a decade, to basically devise strategies to maximize the sensitivity given the complexity of the final state. So what we concluded is that we would have to basically devise a bunch of control samples in a way that would minimize the theoretical uncertainties for those extrapolations, where the normalization of the backgrounds would come from control samples, and the extrapolations based on ratios would have the least amount of theoretical uncertainty. And that is basically done for each background separately, and each background has its own idiosyncrasy and it has its own theoretical uncertainties. And this was all done very carefully so as to minimize the theoretical uncertainty, to make the search the most robust as we possibly could at the time. And basically, this is one of the final products. You have here actually zero. There was a contribution from one jet. I have to correct myself here, but the dominant sensitivity really came from the zero jets. You can see here that there's quite a number in red. This is the SM Higgs boson contribution on top of the background. You don't have an environment mass, you have a transverse mass. You remember, we cannot reconstruct the Z components of the neutrinos, only the transverse momentum. So that leaves us with transverse mass distributions to work with. And also there was a lot of optimization in terms of which algorithm we would use. It's not an obvious question really. And it actually took us some time to figure that out. And then we concluded what algorithm we would be using for discovery. You can see here this overwhelming signal here, and overall the transverse mass being consistent with the mass of the Higgs boson, of course, within the accuracy of the measurement. And you see here this spectacular event of an electron and a muon with some missing energy and some depleted hadronic activity. This is one of the spectacular events. Other channels are also very important, in particular the tau and BB bar. But the problem with these channels, the challenge with them is that you cannot reconstruct narrow structures, and also they are not as copiously produced compared to the backgrounds, compared to the other three. But of course, they're playing, and they have played a very important role as well, and especially when it comes to measurements. You see here, especially the tau, because the signal to backgrounds are not great, which first has to do with the structure of the backgrounds and second, with the fact that you cannot reconstruct a narrow resonance. So the wider the resonance, the more background you have underneath. So that hampers your ability to observe. You see here now a typical distribution of how the invariant mass of the TT bar system looks like. And you typically can do that only in boosted topologies, whether it is induced by vector boson fusion or high PT boosted topologies. And that's where you have some sensitivity for the Higgs boson. And the BB bar is even more complicated. All right, so let's move on to the mass measurement. And this is one of the first measurements made. As already indicated, the mass, of course, will be most accurately measured with the structures in the diphoton and 4-lepton invariant mass spectra that you saw. This was now with more data compared to the discovery. This is the famous combination that Atlas and CMS did with the entire round one data. Remember, the discovery wasn't using the entire round one data set. And then you see here the different measurements by Atlas and CMS in diphotons and 4-leptons, the corresponding combinations. You had teams of people working together from Atlas and CMS. And the corresponding Atlas CMS combinations of diphotons and 4-leptons here, very compatible with each other. And the overall combination, with just the run one data set, given a stunning accuracy of 0.2%, that really forces theory to work very hard, basically in trying to understand or interpret basically that mass. For instance, if you talk about BSM scenarios, that 0.2 is a very strong accuracy. And in terms of uncertainties, I mean, these measurements are, most of the work goes into understanding the experimental uncertainties that go into the reconstruction of invariant mass, because you really need to understand the energy and the position of the photons very well, and the electrons and the muons extremely well. And what you do, you have a statistical apparatus that through nuisance parameters that allows you to assign the uncertainty to each of the sources of uncertainty. So to say, what you can clearly see that at the top, the biggest contribution on to the measured mass comes from the non-linearity, non-energy linearity of photons in Atlas and CMS. And I have to say, this is really the result of decades of work of people designing detectors, installing, calibrating, understanding. It's really a very complex chain. It looks like it's just one graph, but what really goes into it is a massive amount of work from hundreds of people to really understand this. So this is really a major highlight in terms of the results of the Large Hadron Collider experiments. All right, so let's talk about coupling strength. So this is now you go from observation to trying to do the best you can to understand coupling. So how the Higgs boson that we observe couples to the standard model. Of course, as we know, proton-proton collisions have limitations, and obviously it would be ideal to have an E-plus machine to achieve high precision, but you basically do what you can with the data you've got, and a lot has been done in this space. So one way that has been adopted by both of the experiments is to assume that the possible deviations of the coupling of the Higgs boson to the standard models are basically driven by dimensionless modifiers. Okay, so what you basically assume, what you measure, is what we refer to as the kappa framework, is that these kappa modifiers are basically dimensionless, and that what you're trying to establish is basically possible deviations of the data and interpret them from the point of view of couplings that would deviate from unity, but that would have the same CP structure as in the standard model. Okay, and that is basically obviously an advantage, but also a drawback of this approach. As you will see later, the moment you become slightly more sophisticated in introducing new physics in those couplings, whereby you would introduce a different CP structure into the couplings, that the whole system of kinematics changes in a way that you would need, and you need a much more sophisticated apparatus to do this. But at the time, this was basically a very good first approach. People think and do, especially theorists, much more sophisticated and more general study of the couplings. But so far, I'm going to show what we refer to as the kappa framework. So in this kappa framework, you assume that the structure of the couplings or the Higgs to the standard model is as in the standard model, and you only vary the size of that coupling. And then once you do that assumption and take it into account the decays and production mechanism, you basically, everything is parameterized in terms of this dimensionless numbers, these kappa values. And they are denoted with an index that pertains to what you are coupling with. And if you have loops, you basically have a combination of those kappas, and they're basically on the right-hand side. You basically have the corresponding scaling factors. Then you basically collate all the data that you have. I'm giving you all the results. Obviously, there's much more accurate results now, but the point of this talk is not to give a review of the latest results, but basically to walk you through what we do around the Higgs boson. And then what you do, basically, you look at this modifiers and signal strength, so to say, from different standpoints. Here, for instance, you look at the strength when you interpret the data as an addition of certain different production mechanisms, and then you integrate over decays, and then you measure what you see in the data with respect to the standard model through this dimensionless numbers. And then you have mu as the signal strength, and then the kappa modifiers that are related to couplings. And all in all, obviously with big errors, everything seems consistent with the standard model. You can also, what you do is look at decays and then integrate over production mechanisms. And then you have the corresponding signal strengths for photons, diphotons, ZZ, WWs, tau-taus, and BB bar, and with the corresponding dimensionless numbers. Now, one has to bear in mind that when we show the previous one and this one, there's always a caveat, as you saw earlier. Some decay products are looked for not inclusively, meaning you do it topologically, so then you're only sensitive to certain production mechanisms. So it's not like a matrix where that is filled 100% with decays and production mechanisms. So it's a bit more complicated, but obviously this is all done internally in the calculation. You have basically here these results that experimentalists produce, and there's also many phenomenologists working on them. And then you can also present this thing by saying, okay, production mechanisms and decays. So you have the production mechanism, then you split that into different decays, and you obviously, because you run out of stats, your errors become bigger and bigger, but this is also a nice way of presenting these results. You can also present results in terms of ratios. This was suggested already 20 odd years ago, because these are going to cancel certain experimental uncertainties, but also theoretical, and most importantly, the lack of knowledge of the total width that obviously you always have to bear in mind. So when we do all these exercises about extracting coupling, there's always some assumptions that need to be taken into account. One of them is the total width. And then you basically end up having even more numbers and so on and so forth. And this is a lot of work, I have to say. All right, so I think I'm going to move away from this because I'm running out of time. And I'm going to talk about basically the spin CP study, the spin CP quantum numbers. and how these are explored using decays. And remember, Francois Englert was very eager to see that the experiments conclude that what we saw is compatible with the quantum numbers of the standard model. That was the missing piece for a Nobel Prize, which he later got. So you can do these things by studying the decays or studying the production. I'm not going to go over in great level of detail, but suppose if you look at the Higgs boson, you go to the rest frame of the Higgs boson and you have it decaying to Z, you have basically a number of planes. So you have really a lot of leverage in order to understand the CP structure of the Higgs boson and the couplings to weak bosons, and that holds a fundamental meaning. And you can see here, I'm not going to go into the details. You can actually feed everything through a sophisticated statistical apparatus with discriminating variables. And you can see here, when you feed that through a BDT, a machine learning algorithm, you can see here that the two different hypotheses, JP 0 plus, that's the standard model hypothesis, ping 0 parity plus, how different it is compared to the dashed line on the right-hand side of a non-standard model assumption. Now, it's important to note that what was done at this stage, and to some degree continues to be done, is to rule out a 100% hypothesis. So when we say 0 plus or 2 or 2 plus or 2 minus, all the combination that we have with spin 2, we're basically ruling out that the Higgs boson is 100%, has 100% of those quantum numbers. So let's just make that very important distinction. We're not talking about excluding admixtures. That's a much more complicated question. So what you do here is that you use the same statistical apparatus, the likelihood ratio that was developed for the discovery, but now to serve a different purpose. In particular, to establish whether the experimental value measured, or whatever discriminant, as the one I showed earlier, is closer to the standard model hypothesis compared to the BSM hypothesis used. And remember, we don't have time to go through this, but when you have likelihood ratio formalism, you need to have two hypotheses really basically playing against each other. So what you see here is an illustration of what is done here in terms of the likelihood ratio. You have here the distribution in blue of what the outcome of that likelihood ratio would be for a standard model hypothesis, JP0 plus, compared with the corresponding distribution if the hypothesis was 100% 0 minus. You can see here the red distribution. And then the line here, the vertical line, is the experimental observation. Clearly, what you see here is that the experimental observation is closer to the blue line than it is to the red line. And then you argue that the compatibility of the experimental observation with the standard model hypothesis is basically the blue shaded area, and the incompatibility with the BSM hypothesis, in particular 0 minus, is basically this small red area here, which would be, you can view as a p-value, which is what's basically described on the right. And for all the BSM hypothesis, again, assuming 100%, the standard model Higgs, sorry, that the Higgs observed at 125 is 100%, 0 minus, 1 plus, 1 minus, or the version of a spin 2, you can see there the incompatibility, this red area with those hypotheses, and all the hypotheses that Atlas and CMS had considered were incompatible with the data. And the data was always compatible with the standard model hypothesis. That's basically how you look into it. And both Atlas and CMS published their own papers. I'm going to skip all this just to basically emphasize that, for instance, CMS made a very, very sophisticated scan through all the more hypotheses, in particular spin 2. You can clearly see that the observation which is that the data is always closer to and within the 2 sigma of the orange, which is the standard model, and then at least 2 sigma away from the blue, which is different versions of a spin 2 hypothesis. So that sort of like gives you a feeling of the span of this study. All right, and in my remaining few minutes, so that we can have some time for questions, I'll talk about the same question now, but for the point of view of production. You, of course, can look at the properties and the kinematics of the decays. You can also look at the kinematics of certain production mechanisms, for instance, vector boson fusion. And in a sense, you're looking at the same thing. You know, you can basically turn this picture on the left to this picture on the right, and essentially trying to pin down the same thing. Okay. Now, needless to say, because we have a much cleaner environment in the decay of 4 leptons, obviously that is statistically superior and the sensitivity superior compared to the production, but that doesn't mean that we cannot do it. And basically, vector boson fusion plays a very important role. If you look at if you fold the rapidity or pseudo rapidity azimuthal angle plane, so that's your detector, it's sort of like a cylinder that you folded on the plane. What you see is that in the standard model, because of the specifics of the couplings of the standard model Higgs to W's and Z's, what you have is a very striking signature. And this plays a very important role in Higgs physics, in that the scattered quarks are going to be widely separated. They're typically going to be in opposite hemispheres. And there's going to be a big rapidity gap with not a lot of hadronic activity, because you have the exchange of colorless particles between the quark lines. And then you typically have the decay product somewhere in between. So it's a very striking topology that, as you will see in a minute, is very sensitive to neophysics. The moment you mess with the coupling, the kinematics and the correlations of this final state change dramatically, as you will see in a minute. This is a famous paper by T.Plehn, D.Rainwater, and D.Zeppenfeld. They first looked at the phi correlation between the jets, who really are able to separate standard model from a pure CP odd or a pure BSM CP even hypothesis. And basically what you do, you can write down these high dimensional operators, CP conserving and CP violating, and then you basically start varying the lambdas on those parameters to really see how it affects the final state. And based it's more a non-standard model-like structure of the couplings. Basically, you know, an illustration of how different the standard model is compared to BSM hypothesis at the level of production. In vector boson fusion, if you were to assume different kinds of couplings and different spin, basic different spins, different CP states or structures, excuse me. And you have basically, just to illustrate the situation here, this is, if you look at the vector boson fusion, you see here on the upper left graph, the standard model in vector boson fusion. You see here the opening in rapidity, or the difference in rapidity of the 2 jets, and on the y-axis and on the x-axis you have the square root of the product of the transverse momentum of the struck quarks. You can see clearly that the standard model has a very clear preference as to where and how the phase space is populated. But the moment you actually look at the 2 graphs below, you change the structure of those couplings, you see a very drastic change in how the phase space populated, and that you exploit just like you did when we looked at decays, but at the level of production. This is for vector boson fusion. You can also look at associated production with a Z or a W. You can clearly see the differences between the different assumptions. You can see here, for instance, and I think this is my last slide, that if you do the same thing, but now you look at the Higgs being produced of the stratum of a W or a Z, if you change the type of coupling that the Higgs has with the Ws, for instance, you are going to create a very different distribution. For instance, on the left, on the lower left, you have the invariant mass of the Higgs and the weak boson. On the right, you have the transverse momentum of the Higgs. So they change quite significantly. So when you put everything in context, you can certainly, the study of the decays and the study of the production can help you pin down to the best of our abilities the possible, non-SM composition of the Higgs boson. And I think I'm going to leave it here. And I've posted some questions. Thank you very much.
Thank you very much to you, Bruce, for this overview of the Higgs physics and experimental results in that. Are there questions already right now?
Now, I've posted 4 questions here, so we can discuss them later.
Right. Yes. So I also don't see any other questions in the chat or any hands raised yet. So everyone can take the afternoon to digest this a little bit and think about whether they have further questions. And Bruce, you're also going to be around in the recitation session tonight. Is that correct?
Yes, I will.
So if there are any further questions that pop up, people can get into discussion with you. Just to mention again, we're going to have a bit of a special format of the discussion session in the recitation tonight, namely a plenary Q&A session, which takes place at 8 p.m. in the lecture hall in the Gather space. And after that plenary Q&A session with the lecturers from D.Phyn about the career perspectives outside of academia, we can then break up and find the lecturers to discuss any questions about the other lectures also of the day. So yeah. Right, then thanks everyone, and thanks Bruce again. And we will take a break of half an hour and see everyone on the half hour with our last lecture on industrial applications. See you then.